Good morning, students. I hope you are well. Today we are going to see series RLC circuit. So last class we have seen AC circuit containing resistor, AC circuit containing inductor, AC circuit containing capacitor. And also we have seen that when an AC circuit is having resistor, then current and voltage are in phase with each other. There is no phase difference between current and voltage. Similarly, when an AC circuit is having inductor, voltage is leading the current by pi by 2, or current is lagging the voltage by pi by 2. And similarly, when an AC circuit is having capacitor, then current is leading the voltage by pi by 2, or voltage is lagging the current by pi by 2. So we have seen separately each thing. Now we are going to see an AC circuit containing resistor, inductor and capacitor. So when an AC circuit is having all the three components connected in series, then it is called as series RLC circuit. So we are going to analyze the phase relation between current and voltage in an RLC circuit. So let us consider an AC circuit connected to a resistor, inductor and a capacitor. So we are having resistor of resistance R ohm, inductor of self-inductance L and a capacitor of capacitance C. All the three components are connected in series. So resistance is suffering resistance R ohm. In a similar way, the opposition offered by the inductor for the flow of current is called as inductive reactance. Inductive reactance is XL ohm. And similarly, the opposition offered by the capacitor for the flow of current through it is capacitive reactance. So, all the three are similar to a resistor. And we know that when several resistors are connected in series, current through the resistors remains the same. So in a similar way, same current flows through resistor, inductor and capacitor. The current which flows through the resistor will also flow through the inductor. The current which flows through the inductor will also flow through the capacitor. But the voltage difference across the resistor, inductor and capacitor differs. So let us consider the voltage difference across the resistor be VR. So VR is the potential difference or voltage across the resistor. In a similar way, VL is the voltage difference across the inductor. And similarly, VC is the voltage difference across the capacitor, and V is the net voltage difference across all the three components. Next, what we are going to do, we are going to construct a phasor diagram and we are going to see the phase relation between current and voltage. So for that, we are going to construct a phasor diagram. So we are going to consider a phasor diagram. So origin. I am going to represent the current through all the three components as OI. So OI is the current, and it makes an angle of omega t along the baseline. So omega t. Let us now consider resistor. We know current and voltage are in phase across the resistor. So the voltage across the resistor is represented by OA. So OI is one phasor and OA is another phasor. OI is representing the current and OA is representing the voltage across the resistor. So this phasor OI and OA are in phase with each other. That is, the current and voltage are in phase across the resistor. Next, come to the inductor. So you know, across the inductor, voltage is leading the current by pi by 2. So current through the inductor is OI. Potential difference or voltage across the inductor is represented by VL. This VL is leading the current by pi by 2. So I am representing this VL by a phasor OB. OB is nothing but voltage across the inductor. So this OB is 90 degree out of phase with OI. So voltage is leading the current by pi by 2. Next we are going to see capacitor. Across the capacitor, current is leading the voltage or voltage is lagging the current. So VC is the voltage across the capacitor. This voltage across the capacitor is lagging the current by pi by 2. So I am representing it by a phasor OC. So OC represents voltage across the capacitor and this voltage is lagging the current by pi by 2. So this phasor diagram gives the phase relation between current and voltage across the three components. So across resistor, current and voltage are in phase. So phase difference is 0. Across the inductor, voltage is leading the current by pi by 2. Across the capacitor, voltage is lagging the current by pi by 2. So this phasor diagram tells about the phase difference between current and voltage across the three components connected to this AC source. Now we are going to find out what is the resultant voltage across the three components. So now let us suppose consider in this RLC circuit the value of VL is greater than VC, that is voltage across the inductor is greater than voltage across the capacitor. For our analysis we are taking like that. So these are two vectors. These two vectors are opposite vectors and the resultant vector is obtained by subtracting VC from VL. So I am representing this VC minus VL minus VC is the resultant of OB minus OC. So I am representing it by OD. So OD is the resultant vector of, so OD is the vector which is the difference of OB vector minus OC vector. So now we are having two voltage vectors. One is VR and one other one is VL minus VC. So these are the two voltage vectors. Now the resultant of this vector can be obtained by using parallelogram laws of vectors. So what are these parallelogram laws of vectors says? If two vectors, so I am having two vectors. If two vectors forms the adjacent side of a parallelogram, the diagonal passing through the two vectors will give the resultant vector. So this is one vector, that is BP vector, and this is PQ vector. So the resultant vector is given by the diagonal. So this is parallelogram laws of vector. So by applying parallelogram laws of vector with OA and OD as the two sides of the parallelogram, you complete the parallelogram. So when we complete the parallelogram, the diagonal will give the resultant vector. So the resultant vector is given by OE. What is this resultant vector gives? This resultant vector gives the resultant voltage. So let the resultant voltage makes an angle phi with OA. So now, according to the parallelogram laws of vector, the resultant vector is given by square root of P square plus Q square plus 2PQ cos theta. So this is the formula to find the resultant vector according to the parallelogram laws of vector. Now we are going to apply it. When we apply it, the resultant vector is V. So V vector is equal to square root of OA square, that is VR square, plus OB square, OD square, that is VL minus VC the whole square, plus the third term will become 0 here. Why it becomes 0? Because cos 90 is equal to 0. So this term will become 0. So the resultant vector V is equal to VR square plus VL minus VC the whole square. So substituting the value, VR according to Ohm's law, V is equal to IR. That is, I into I is equal, V is equal to IR, I into R. And similarly, VL is equal to I into XL. VC is equal to I into XC. Substituting these values, we will have square root of I or the whole square plus I into XL minus I into XC the whole square, taking I outside, so I into square root of R square plus XL minus XC the whole square. This is the resultant voltage. So resultant voltage is equal to square root of R square plus XL minus XC the whole square. According to Ohm's law, V V by I. So V by I is equal to square root of R square plus XL minus XC the whole square. This V by I is called impedance Z. So impedance Z is equal to square root of R square plus XL minus XC the whole square. So this expression gives the impedance of the RLC circuit. So what is called impedance of the RLC circuit? It is the net opposition offered by resistor, inductor and capacitor connected to the AC circuit. The net opposition offered by all the three components connected to the AC circuit is called impedance of the circuit, and the impedance is given by Z is equal to square root of R square plus XL minus XC the whole square, and the resultant angle pi can be obtained by constructing voltage triangle and impedance triangle. So I am having O, this is VR, this is VL minus VC, this is V, this is pi, and the corresponding impedance triangle is this is resistance, this is XL minus XC, and this is Z. So from this triangle we can find tan pi. So tan pi is equal to opposite side by adjacent side, that is VL minus VC by VR. So that is equal to XL minus XC by R. So tan pi is given by pi is equal to tan inverse of XL minus XC by R. This equation gives the angle of the impedance. So next we are going to see what are the special cases in it. So the phase angle is given by tan pi is equal to XL minus XC by R. Now when XL is greater than XC, when XL is greater than XC, pi is positive. Pi is positive. So the phase angle is positive. Then the circuit is said to be inductive, purely inductive. So if the circuit is inductive means voltage will lead the current or current will lag the voltage. So corresponding voltage is given by V is equal to Vm into sin omega t, and the corresponding current is given by I is equal to Im into sin omega t minus pi. So the circuit is purely inductive. This is case 1. So when XL is greater than XC, the circuit is inductive. Circuit is inductive. So pi is positive. Pi is positive means voltage will lead the current or current will lag the voltage. Then the corresponding voltage and current is given by V is equal to Vm into sin omega t, and the current is given by I is equal to Im into sin omega t minus pi. Second case, when XL is less than XC, since capacitive reactance is greater than inductive reactance, circuit is capacitive. Since the circuit is capacitive, pi is negative. Pi is negative. Pi is negative because XL minus XC is negative. So XL minus XC is negative, pi is also negative. So circuit is capacitive. If the circuit is capacitive means current will lead the voltage or voltage will lag the current. Then the corresponding voltage and current is given by V is equal to Vm into sin omega t, and current is given by I is equal to Im into sin omega t plus phi. Third case, when XL is equal to XC. When XL is equal to XC, XL minus XC becomes 0. So, when XL minus XC becomes 0, then the circuit is resistive. So, since the circuit is resistive, voltage and current are, so phi is equal to 0. So, phase difference is 0 means circuit is resistive. If the circuit is resistive means current and voltage are in phase with each other. The corresponding voltage is given by V is equal to Vm into sin omega t, and the current is given by I is equal to Im into sin omega t. So these are the three cases. When XL is greater than XC, XL minus XC is positive. XL minus XC is positive means pi is also positive. Since XL is greater than XC, circuit is inductive. If the circuit is inductive means voltage will lead the current. Corresponding voltage and current is given by V is equal to Vm into sin omega t, I is equal to Im into sin omega t minus pi. Second case, when XL is less than XC, XL minus XC is negative. XL minus XC is negative means pi is also negative. In that case, the circuit is capacitive. Since the circuit is capacitive, current will lead the voltage. So voltage and current on the circuit is given by V is equal to Vm into sin omega t, and the corresponding current in that circuit is given by I is equal to Im into sin omega t plus pi. When XL and XC are equal, XL minus XC is equal to 0. Then pi is also 0. If pi is 0 means phase difference is 0. Phase difference is 0 means then the circuit is resistive. So voltage and current are in phase with each other. And the corresponding voltage current is given by V is equal to Vm into sin omega t, I is equal to Im into sin omega t. Next we are going to see resonance in series RLC circuit. So what is called resonance? When any object vibrate with the natural frequency and it makes any object very near to it to vibrate with the same frequency as that of the natural frequency, then the two bodies are said to be in resonance. Once again I repeat, when a body vibrates with its natural frequency, that vibrating body makes another body to vibrate with the same frequency, then the two bodies are said to be in resonance. So now we are going to see what is resonance in RLC circuit. When the frequency of the applied voltage is equal to the natural frequency of the RLC circuit. So the frequency of the RLC circuit is given by RLC circuit frequency is given by omega is equal to 1 by root of LC. This is the natural frequency of the RLC circuit. If the frequency of the applied voltage is equal to the natural frequency of the RLC circuit, then the current through the RLC circuit is maximum and the impedance becomes minimum. This condition is called as resonance in RLC circuit. So when this will happen? Current through the RLC circuit is given by I is equal to V by Z. According to Ohm's law, I is equal to V by R. But in the case of RLC circuit, this resistance is represented by impedance. So current through the RLC circuit is given by V by Z, where Z is equal to, that is V by square root of R square plus XL minus XC the whole square. So when the current will become maximum, impedance becomes minimum. When this impedance becomes minimum, when the frequency, applied frequency of the AC voltage is equal to the natural frequency. That condition is called as resonance, because at that time the current through the resonance circuit is RLC circuit is maximum. So this is the natural frequency of the RLC circuit. So omega is equal to 1 by root of LC, or omega square is equal to 1 by LC, or omega into L is equal to 1 by C omega. What is L omega? L omega is nothing but XL, inductive reactance. What is 1 by C omega? It is nothing but capacitive reactance. So when XL is equal to XC, the impedance becomes minimum. So when you substitute this condition here, we will have I is equal to V by R. So the impedance of the RLC circuit is minimum. At that time, maximum current flows through the RLC circuit, and this condition is called as resonance. The frequency at which resonance takes place is called as the resonance frequency. So resonance frequency omega R is equal to 1 by root of LC. So this angular frequency is equal to 2 pi mu R. So 2 pi mu R is equal to 1 by root of LC, or mu R is equal to 1 by 2 pi into root of LC. So this expression will give the resonance frequency. The expression given by this, the frequency given by this expression is equal to the frequency of the applied voltage. So when this frequency is equal to the frequency of the applied voltage, at that time the impedance of the RLC circuit is minimum and a maximum current flows through the RLC circuit. This condition is called as resonance. Usually when we see, the frequency depends upon the value of capacitor and inductor. So usually the resonance condition in RLC circuit is obtained by varying the value of L and C. So when we vary the value of L and C, at one particular value of L and C, XL is equal to XC. At that time, the impedance of the RLC circuit is minimum and heavy current flows through the RLC circuit. Thus, resonance condition is achieved in RLC circuit. So next we are going to see what are the effects of resonance in RLC circuit. So there is resonance condition in RLC circuits are used in many applications. Filters, voltage multipliers, and many other applications in electronics. One of the important application of resonance in RLC circuit is applied in radio and television for tuning. So in radio and television, we are using this concept of resonance in RLC circuit. You know, different radio station and TV station, while they are broadcasting, they will broadcast at different frequency. So every radio station or a TV station will broadcast their program using electromagnetic wave of particular frequency, and they will send this electromagnetic waves in space. So in air we are having large number of electromagnetic waves of different frequency that were sent by different broadcasting station. In our radio or television set, we are having RLC circuit. In this RLC circuit, the value of inductive reactance is kept constant and the capacitive reactance is varied. So when you see, that depends upon frequency. This inductive reactant and capacitive reactant depends upon frequency. Frequency depends upon inductance or capacitance. So usually in tuning set, what they used to do, the value of C is varied using parallel plate capacitor. Variable parallel plate capacitor is used in the RLC circuit. So when they vary the value of capacitance, this frequency will change. When this frequency is nearly equal to the frequency of the electromagnetic wave sent by a particular station, then the current through the RLC circuit is maximum. Then the receiver in that radio or television will respond only to that particular frequency and pick up the particular frequency which is equal to the frequency of the RLC circuit. So once again repeat, in tuning circuit what they used to do, they use variable plate capacitor and they vary the capacitance. When the capacitance value varies, frequency gets varied. When this frequency produced by the RLC circuit is nearly equal to the frequency of the signal transmitted by a particular radio or television station, then what will happen? That receiver set will respond only to that particular frequency of the signal and it will pick up. So that's RLC circuit is used as a tuning circuit in radio and television. So next we are going to see quality factor. What is called quality factor? So last session we have seen that in an RLC circuit, at resonance condition, the impedance of the circuit becomes minimum and therefore the current through the circuit becomes maximum. So at resonance condition, the current through the RLC circuit will increase. Due to this increase in current, there will also be increase in voltage across the inductor or capacitor. So the quality factor tells us magnification of the voltage across the inductor or capacitor, how many times the magnification as that of the applied voltage. That is called quality factor. So quality factor is nothing but it will tell the magnification of voltage across the inductor or capacitor compared to the applied voltage. So quality factor is defined as quality factor Q is equal to voltage across inductor or capacitor by applied voltage. Applied voltage. You know, at resonance condition, since XL is equal to XC, this applied voltage is equal to the voltage across the resistor. So voltage across L or C is given by, suppose if we consider L, so voltage is equal to current into impedance by applied voltage is equal to I into R. So cancelling this we will have XL by R. But we know XL is equal to L omega by R. Since this resonance condition is taking place at resonant frequency, we will have L into omega R by R. But omega R is equal to 1 by root of LC. So substituting this value, we will have quality factor Q is equal to L by R into 1 by root of LC. So that is equal to 1 by R into root of L square by LC. So we will have quality factor is equal to 1 by R into root of L by C. So this will gives the expression for the quality factor. So quality factor is nothing but it tells about the magnification of the voltage across the inductor or capacitor compared to the applied voltage. So this will gives the quality factor, and the quality factor is given by Q is equal to 1 by R into root of L by C.